Okay, so yeah, one second. I'm just trying to see what's the problem. Okay, now it's sharing. Yeah, so I think this is the first of the course for Cassandra, and we'll get started now. So today's focus would be more at the fundamentals of NoSQL. We'll look at the landscape of NoSQL in general, cover the CAP theorem, understand the key characteristics of NoSQL database, and then explore a bit of acid versus base. That should pretty much look at the fundamentals of NoSQL. That might take a little longer than 1 hour, but yeah, if there is more time around, we will we'll look at the introduction to Cassandra today, and then maybe start from there into more details from there on. So today's is going to be more fundamental, and the whole idea is to establish the base so that from the next course on the class onwards, we should be able to look at Cassandra in more details. So let's get started. So if you look at any of the database systems today, before NoSQL has arrived, what would be our reaction? So I have tried to put that in one single picture to see that when we start thinking of any applications, we need to start storing data. And to store the data, the immediate thing which we say is, okay, I need a file or a database. File you would typically avoid and look for only storing a video file or image file or something like that. But anytime you have a data, you will immediately think of RDBMS, and that would be the proprietary or the monopoly in this data storage space, and that has been the rule till date. So the idea is what really has changed from here on, so that NoSQL have started coming up. So to do that, first we need to look at what are the challenges which a NoSQL or a RDBMS brings in, so that we appreciate why a NoSQL is really needed. So any of you had any experience in what the challenges in RDBMS are? Anybody want to take a stab? Yeah, so you can unmute yourself for sometimes, if as long as the echo doesn't happen, we are fine. We can have that interaction. So I see. Yeah. So or you could type in the chat window. Either way is fine, so that I could see that. Yeah. So unstructured data. The way to handle unstructured data is what Ravi is mentioning. The size, unstructured data. So those are certain things which has definitely resulted into the limitations of RDBMS. So let's look at a typical web application. A web application where it's a typical website which we want to render. And to render a website, what we do is we need a data store which will store the data for the website. We need the data of the sessions. We need the data for maybe the transactions which are happening in the site. We talk about user login profile details and many other interactions on the site itself. So the whole idea is that all this data needs to be stored. Correct. So that is the construct when we are looking from a website perspective. Now, as the website grows, you see that the volume increases, and the natural choice for any database is to start scaling it up. So first you would have a small machine which hosts the database. Then as the size increases or the performance starts deteriorating, you will say, oh, I need more CPU, more memory. So let me bring up a bigger machine, install the database on that. The other option would be somebody would say, okay, Oracle RAC and others are giving some fancy clustering solution. So why don't I use that? In all these solutions, what we are doing is the cost is going exponentially up because the technology is proprietary and the technology is not horizontally scaling. It is not horizontally scaling. We are trying to apply lot of vertical scaling concepts, and some amount of horizontal scaling is what we are trying to do. Okay. So the first thing is we try to horizontally scale the application in some form. Okay, and then the main construct which is there is that the database has to be more and more scalable, and volume keeps on increasing. So in a traditional RDBMS, what we do, we try to partition the data, we try to shred the data, we try to distribute the data in different machines and try to run the queries on these distributed machines. But the problem with that is we have tried to create a database systems where each of those machines are not fault tolerant at all. So if one shard goes down, then you need to see, okay, what happens. So you need to bring up another shard, copy all the data there, make it replicatable and available, which essentially means now you are getting into the next territory where as data increases, what you are doing is you are trying to shred it, you are trying to replicate it, now you are trying to even manage that distributed system, and you get into the problem of distributed systems. So that's where traditionally RDBMS scaling really reaches, and it becomes unmanageable at one point of time. So that's one line of thought. Okay, so let me summarize once again that same line of thought, where a typical RDBMS application is working fine under low loads. Volume increases. We try to scale it by shredding, replicating the shreds, and then we get into the problem of managing the distributed system itself. And the RDBMS, since it tries to maintain that ACID property, that is atomicity, consistency, integrity and durability, the stress on that RDBMS system is very, very high, because to manage a distributed database and still get ACID property is very, very difficult, and at one point it becomes really impossible to scale further. So that's the challenge, that replications are not online replications, because replications are only for offline. Because if you replicate on an online in an RDBMS system, the key problem is consistency will be a problem. You will not be able to guarantee consistency as soon as you start replicating in an RDBMS system. So most of the RDBMS system try to do an offline backup or an online backup, but it is not an used backup. It's only one disk which is where the data is written, and that is pretty much what it is used. The other is pretty much for when the node fails, okay, we'll switch over, and after some recovery. So that's the kind of model. So fundamental problem is replication. So if you start replicating the data, which essentially means your consistency is going for a toss, and that's one fundamental problem of RDBMS. RDBMS, as it starts to scale, the problem starts to become more and more evident. So this is one line of thread. Volume has increased. Now what's the second line of thread? If you look at the second line of thread, is applications profiles has changed. We are not talking anymore about only financial transaction where ACID is always required. We are talking about databases and applications, let's say the new generation of applications, where the demand for ACID is not very high. So that's another set of application which is emerging. While the volume is increasing, the usage profile of the application is also changing. So that's the second thing which is happening in this space. And the third thing which is really happening around is the emergence of distributed systems. So we have now been able to master these distributed systems and create out patterns in these distributed systems, that now people have started thinking that if we have to do a distributed system or build a distributed application, there are a lot of frameworks already available. So we are trying to simplify the fault tolerance part of it. We are looking at node failure detection. We are looking at leader election algorithms. So all those has started evolving, and that is also another trend which is coming up. So these are the three trends which is converging, and why NoSQL is coming up in a big way. So three things which we talked about. One, the data is increasing. Second, the usage profile of the data applications are changing. And third, the distributed systems are maturing. So these three constructs are driving the promotion of NoSQL. So let's look further detail into it. So let's look at in more detail what are the challenges of an RDBMS system. First, we said we have data growing. So when data grows, what really happens? Your join complexities becomes more and more, because once you shard it and you start putting it in a different partition, now the join can be only on a partition key. If you have a complex join, that whole philosophy becomes a problem. So that's where things starts breaking up for RDBMS, where volume increases. We still need to write complex query, but all the joins has to be forced on the partition key. So that's one place where RDBMS starts to buckle up. The second part is when we are trying to partition it, we try to replicate it. The moment we start replicating, distributed transaction management becomes a problem, because to guarantee atomicity, the basic construct is that you should be able to guarantee transactions across the cluster, which essentially means you need to have a distributed transaction management, where the commit and rollbacks has to be guarded closely till the data is replicated in all the machines in the cluster or wherever the replicas are done. So that is another big challenge which comes in with RDBMS, and the problem is the RDBMS makes it very, very hard because of the relational structure and the way the RDBMS stores the data. So, and the guarantee that it will always give you ACID, that guarantee plus the relational structure plus the replication is making this philosophy a big problem. So that's where challenges with scaling RDBMS becomes a problem. Otherwise it was not that problem. Then as you get into this complexity, there are RDBMS which try to solve this, but they charge a very premium price for it. And that's where when the volume increases, the cost per terabyte of storage for any data becomes very high. So when you look at RDBMS problems, first you check it, what is the cost per terabyte? And if the cost per terabyte starts to move exponentially higher, that's where we realize that this RDBMS now has to be done something. So this is one leading indicator. When the cost per terabyte for your storage becomes high, you need to start looking at alternatives. And that's precisely what happened with all these startups, where the cost per terabyte was something which was unmanageable for them, especially being a startup as well. The second aspect is the data is growing exponentially, and they have no control on the growth of the data. So it's pretty much internet facing application. The growth is pretty much user dependent, and as it grows, managing an RDBMS will really not be a viable solution. The last part of it we already covered. The whole idea is about workload and usage profile. So the web application which we are talking about, it has a different usage profile versus a banking application, and the need for ACID is not very high, and that's what we are trying to say. The need for ACID to ensure that every transaction has to commit at the same time is not something which is very important. So for an Facebook updates, we always says that yeah, if the comment appears maybe a second or a minute later to other person, it doesn't really matter. Even in a LinkedIn or any social application, it is highly immaterial if the data reaches the other user on a consistent model in maybe a second or a minute later. It is still okay as long as the data reaches there and it will not be showing anything wrong. It's not showing somebody else's data. As long as it's showing the right data, after some time it's okay. The only thing is it will have some missing updates. That's the only thing which will show up there. So those kind of trade-offs is what is being looked up to bring the cost per terabyte down, and that's where the challenges of RDBMS exist. So I'll pause here. We can discuss a few more items if you have, and then we'll move to the next part. Any questions? Okay, so let me summarize one last time. So what we did till now, what we said is RDBMS has been the only storage till now. 3 trends emerged from there. Volume is growing up. Second, the usage profiles are changing drastically, and the third part is we need to look at distributing. As we start distributing, the challenges of RDBMS goes manifold. So these are the 3 things we looked at. Cost per terabyte is the only measure which you need to start looking at when your cost goes up per terabyte of storage. You really see that yeah, there is some problem, and you need to find alternatives. So there is one more. Yeah. So let's look at this game of transaction and RDBMS a little bit more, and see what ranges we see things moving around. Okay. So if you see the left side picture, we are saying that yeah, less than 10 million transactions. Yeah, looks like an OLTP. Hello? Is the voice clear now? Is the voice okay? Anybody? Okay, fine. Yeah, so we'll look at this aspect. So there is one is volume aspect, and that's what I tried to represent on the left side of it. So less than 10 million we say OLTP. As transaction goes to 100 million ranges, we see that traditionally in a data warehouse we have been able to handle, and that's at that typical range RDBMS has been operating, and it's been working okay as of now. It's not that it's the most optimal use of it, but yeah, it still works. So you would see that in this range from 10 to 100 million, the OLTP and DW ranges, and traditionally we have been using RDBMS. But the moment volume increases beyond that, now the storage and other things becomes a bigger concern, and then the cost per terabyte starts increasing exponentially. Till here the cost per terabyte might not be that pinchy, but the moment it reaches here, the cost per terabyte starts going very, very high, and that's where the NoSQL and others have started coming up. So to reduce the cost, the same way, the more volume increases, till here it's okay. The more it increases, the guarantee for assets becomes very, very low. And you would say that in a data warehouse system, you really don't need ACID, because only in transactional systems you would need an ACID. The moment it reaches data warehouse and beyond, you really don't need the isolation, the durability, the integrity and other things, because it's more at summarization. We start looking at data more aggregatedly. We more look at summarized data, and one or two transactions here and all to arriving a little late is okay. So once the aggregations finally looks okay, it is great, but it is not like up to the minute we are looking at transaction aggregation. So with that constraint, what we see is that as the volume increases, the need for ACID also goes down a lot. But in a traditional system, it's not like in every system the ACID property will go down as the volume increases, because if the bank is expanding large, the requirement for ACID at the transaction level also will increase. So that is not the point here. The traditional databases, we operate out of OLTP and data warehouse. Now the data warehouse doesn't require that we have ACID properties available, and anything beyond that also doesn't really need ACID at a majority of the things. So we are trying to compromise ACID. That's one thing which we need to look. The second thing is the schema. Now if you look at RDBMS, first we have to say this is the data which I am going to store. This is the structure which I have, and precisely this is where I am going to store the data. So before you store the data in an RDBMS, you should know the schema, and you should know what data you are going to store. Now if the data changes, you have to go back to the drawing board. You start changing the schema, and then try to adjust the schema, deploy those changed schema, and build the application again. Correct? So that's the process. So if you see, now the organizations are becoming very, very schema bound, which essentially what the gist of it is, in an RDBMS world, schema is the king. Everything has to first go to the schema, and you define the schema, then we bring the data. But as the things are moving further, we don't know what data we are going to store. We only know that there will be some data we want to store and some structure to that data, but we'll never know the precise definition of the data and precise attributes of the data which we are going to store. So in such a case, the RDBMS cycle becomes more and more difficult, because you have to go back to the drawing board, you have to create your schema, you have to upload into the system, and then go back. So this whole things becomes schema bound, and enterprises are feeling the pain, because the agility of the new development becomes a problem. So that's the schema aspect of it. So apart from the volume increasing, there is an increasing need to get rid of this schema bound problem. What people really want is, I will bring my data, I will store the data, then I will decide how I will use that data. Now in an RDBMS, that concept doesn't exist. You cannot bring the data till you know how to store the data, how to structure the data. Correct? But in a NoSQL, that is not the case. In a NoSQL, you can bring your data, you can store the data, and then decide how you would really use that in some form or the other, and then you can do flexible schema as and when new fields arrive. So that's the key difference. Any questions on the schema? Yeah, so I think we have covered few things now. The first thing which we covered is the limitations. Then we looked at the volume, and now we have come to the schema. So schema is another problem in RDBMS. And what we are saying with the schema part is you don't have predefined schemas when the data arrives. So once the data arrives, you will decide, okay, there is another 2 columns, can I add it? So that's one thing which will happen. Okay, so let's look at a real-time example which will make it more and more useful. Okay, so we are building, let's say, an application which is doing a weblog parsing or a clickstream analysis. So that's we can do either of that. So let's start with the weblog analytics application. So what happened is we have built a website, and we decided that we want to do some analytics on the website. So first thing it naturally comes out is, let's look at who are the most frequent users who is coming to the website. Then so for that, there you need users, you need who visited it, when he visited it, and which page he visited it. So these are the 3 things which you will store, and you would have modeled it. Now, if you look at in that, there may be another 20 reports which the business user would have really looked at, and he would have modeled all that report. But now the technologies have advanced. Now today I can predict whether that user is going to come next time or not, and if he comes, which page he is more likely to go. Okay. So now the dimension is shifting. Earlier we were just trying to do an analytics on what he has done. So the model was defined, the data was loaded. But now it has changed to the predictive modeling, where now I need to see how can I model a system where we will have to start predicting that the user is coming. So which essentially means we need to do some pattern matching, we need to do some recommendations on the data. Now for that you will say that, okay, I also want to capture his session ID, or I want to capture what his friends in the social networks are. So now you start relating that particular guy and his network together. So you need to start enhancing the data model to say that, okay, now I need what is his social media handles, and then it is not one handle, it is like another 20 handles, because there are 20 social media sites. Now for each of the sites, what are the information which we can get? Now some sites will say, I can give you the name and maybe what he does, his interest. The other side might say, okay, I can give you the name and maybe his location. The other side would say, okay, I'll give you name and maybe his previous job history, let's say LinkedIn. Okay. So if you are looking at these kind of different dimensions of data and you have to start modeling, the data modeler will go crazy. Say that, boss, how do I model all this? Because tomorrow you will bring one more side and say, okay, now I will give you the user and what is interest in the field of maybe economics or in the field of the product, or what he has brought in another site. So if the data keeps changing like this, then how do I model and keep the entire schema upfront? So that becomes a difficulty. So we need a flexible schema where today I'm adding this website, so I know these are 4 fields which I'm going to get. So how I'll model it. Tomorrow another 4 things comes in, I still should be able to model it. So that is one aspect. Now the second aspect is, for all the users, I will not have all the data all the time. Now in a relational database, if you add a column, that much space is wasted for almost every user. That much space is wasted for all users. Now, if you start modeling like that, and you start keeping provision for every user, all the fields, your storage size requirement is going to go up too huge, and all the cost per terabyte is also going to go up, and all these guys are going to make a, so all these guys, oracles and others, are going to make a huge money, because now you have a system where you need to have 20,000 fields which you have modeled on a user, and you have wasted all the space for 90% of the user, because 90% of those sites will not give you data for all the customers. So it is a very sparse distributed data, okay, and there are a lot of fields which needs to be modeled. So given this kind of a situation, how would a data modeler go and build it? And if you have already done data modeling, you know, if you have to model such kind of a situation, it becomes really, really crazy. And we essentially give up, saying that, yeah, this I cannot model, or we will try to force fit into some generic kind of a model, and that then the query complexity becomes too big. So those are the challenges when we are looking at the rigid schema. So two things to look at in a rigid schema. The schema has to be defined upfront. Second, the schema has to be flexible. The schema is not sparse, because once you define the schema, the space is allocated for all the people, so all the fields which we are looking at. And the third part of it is, when you look at the other third part, is where the new data types which are emerging. So now applications are supporting JSON, XML and other things. Now how are I going to store those JSON, XML into my database? Because one of the way to alleviate this dynamic schema problem is to store them in JSON and XML. So in an RDBMS, all you do is you put that in a blob and store it, or you put it in a string and store it. But then your whole query is going to go for a toss, because now you have to do all that JSON parsing or XML parsing in your query, which will become more and more difficult. So if there is a system which helps you store in JSON and query a JSON directly, that will be much more efficient, which will also give you a flexible schema, because JSON by default gives you a elastic or a flexible data store availability. So that's the construct. So three things which again comes up. The data structures are also changing. The flexibility need is increasing, and the need for on-demand schema is becoming more and more prevalent. That's what you would see in the new world. These are the key requirements for, especially with respect to schema. We also looked at the database, the volume aspect of it, and how scalability is going to get impacted. So RDBMS traditionally was not defined to or designed to be distributed. We always looked at vertical scaling as the only option. Add more CPU, add more memory, rather than adding more nodes. Because the challenge is, as you add more nodes, the distributed transaction management becomes a problem, and also replication becomes a problem. So RDBMS was not traditionally designed for distributed scalability. And the last part, which I again mentioned again, saying that the changing user pattern. Now let's look at, there is one more change in user pattern, which is write once and read many times. So this is the traditional plan. Let's say in your Facebook, a kind of an application, you are trying to put a comment once, and thousands of people are seeing that. Similarly, in a Twitter scenario, if you see, you are posting a tweets, and all the people in your links or the networks are able to see it. So it is usually write once and read many times. So that's the new usage pattern which we are seeing. Even in majority of the social sites, the collaboration sites, the whole idea is somebody is creating a content and majority of the people are consuming it. So the usage pattern is now moving from write once, read many times, compared to traditional RDBMS workloads where read write kind of situations were there. So it is not saying that read write situations have gone away. What we are saying is when the volume is increasing and we are seeing that there are large volumes of data being generated, those applications are hardly read write applications. Those applications are usually write once and read many times, like a log analytics application. So if you are looking at a log analytic application or a clickstream application, we never update that data. We are only capturing the data and we are trying to do analytics on the data. So this is one key thing which we need to remember, that the applications which are emerging newly are analytics application, and for analytics application the key characteristics is that you are writing only once and then reading many times. Okay, so I will pause here for a minute. Now I want you guys to speak because I see that a lot of things are coming in the chat, but I am not able to answer at the same time. So it is better that we make it interactive and you speak up. And I am going to just unmute all. So it's better that you guys speak.
Hey, this is Rakesh. Just unrelated question. Is someone recording the session?
Yeah, I think Divakar will be recording.
Okay.
Any other questions?
Divakar, I have a question.
Sorry?
I have a question.
Yeah, go ahead.
I have a question.
Yeah, go ahead.
Even for
I'm not able to hear it.
Hello, are you able to?
Yeah, now it's fine.
See, even in NoSQL databases, analytics, even that case also, storing the weblogs by using schema only will be done, right? Let's say if you are doing analytics for weblog, you
right? Kumar, your voice is pretty breaking, so why don't you type your question? Let me read it out for everybody else. Will that help? Because your voice is fully breaking. While in the meantime, somebody else has a question can talk while Kumar writes it off.
It would be helpful if everyone else mutes if you're not intending to.
Yeah, you can self-mute it, that is better, rather than me muting all, because the moment I mute, almost everybody is going off.
Hey Sudesh, this is Shravan.
Yes,
so we will be given these recorded sessions later, is that correct?
Yes.
Okay, thank you.
So you said that the schema changes unstructured. If if multiple columns are added, the different attributes for a row, and how the calling program knows that these are the attributes which are there, these are the attributes which are not there, or something like that. Like you said that schema changes are volatile, right? How application knows, these are the volatile for this particular key or something like that.
See, so the construct is this applications will not know like this. Okay, it is not like application will dynamically discover and go through. Okay, so now let's say you look at a weblog analytics application itself. the first part of the thing was we have an application and we wanted to do only the basic reporting kind of a reasoning, correct? So you already built an application and that was running, which was reading the data which it needs. Now the second set of requirements on predictive analytics have come through. So you're going to build a new application, correct? But what really happened is you have just enhanced the schema of the old application without impacting the old application, and now the new application can go after that data. So it doesn't really say that the old application now will get impacted. It will not. Okay. Similarly, the old application will not be aware of the application of the new schema which you have added unless you go and change it. Okay. So there is no automatic schema discovery in the sense the application will have to change directly, because the way you will see it is most of these applications NoSQL databases query based on a key. Okay. So in this case it will be the user ID or the session ID or the IP address or something. Okay. So the querying is always going to be based on the key, and we are not fundamentally altering the key as the schema is evolving. The schema is evolving, the attributes are changing, not the fundamental of the particular table itself. If the fundamental of the table is changing, you are adding another table. So in that case, there is nothing big deal. Okay.
So if I understand correct, like if additional attributes are added, like additional columns. So the new rows only can use those new columns. The old rows are still as it is without those columns. You are saying.
Correct. It will be so. If you add any point of time, there is the old rows can actually, if you are creating new records, that in that old table it will still be able to use it, but nobody will see the usage pattern. The usage pattern is always write once, read many times, correct? So since people have written the old data, they are not going to update that data. Okay. So if you are trying to update that data, that will be a huge effort because it's a huge big data which you need to update, and in that case you will reconstruct the whole database itself. So assuming that you are not going to redo the whole thing, only the new data is going to have new fields, which essentially means the table now for any new records which is coming will have the new fields. Okay, and then the application will be able to handle.
So in any case, this alter table is required, alter column family, right? If you want to add additional columns.
See, yes, that is the catch. Now the column family and columns are different. Okay, so in a NoSQL database, we only define the higher level, like the table name. We don't define the columns. Okay, so when we look at the data modeling, you will understand what a column family means and a column means. In Cassandra, you never define what is the column name. Okay, we only define what is the column family name. Okay, so you are saying that okay, in the RDBMS construct, I am only telling which is the table I am going to store the data. The columns will be when the data comes, I am going to put the column name and the value. So it is always name and value which you put in.
Right.
Okay, it. So that alter schema for a new attribute will not work, will not be required. I am saying it is only when you are trying to store a new set of data. Let's say you had a column family called user details. Okay. Now another thing came out is the address of the user came. Okay.
Okay.
So you created saying that okay, address is not going to be used with the user always. So address is going to be used on a standalone model. Then you will create another column family called user address. Okay. And put all the address attributes there. So today you have the zip code in it. Tomorrow you say okay, now I have zip +4 added. So I can just add. As the data comes in, I will add it. It is not like I will define like there is zip code and zip +4. Okay, it doesn't. It will not be.
So it's basically like a string. It can have anything. You are saying.
It is yeah, to some level. So that's where I'll say you hold on the discussion till the model is done. Because
no, I'm trying to.
If I make an attempt to explain it here, then the whole modeling session is what I have to explain. Because storage
because
is not
you're trying to explain that database and the relationship RDBMS. So I'm trying. I couldn't able to because I'm not seeing that exact picture of the this Cassandra or NoSQL. So I'm trying to visualize myself like how it's going to be. So when you are trying to explain me about these differences. So
correct. So what you have to visualize is, for now, assume there is a magical way to represent a data. Okay. So where we only define the table name, we don't define the columns. Okay. Because when we want to store columns, we will say this is a byte. Okay. And the name of this byte is, let's say, zip code. Okay. This attribute is zip code, and the value is this. So everywhere we will put the column name and value, column name, value, column name, value, column name, value.
It's a name value pair. It's basically.
Correct. So the thing is, the data will be stored in name value pair. So there is nothing like a top level column. See, in RDBMS we have saved that space of the name, correct, by defining the column once, column name once.
Okay.
Correct.
Okay.
But in a NoSQL, you will not save that space. The space will eventually get saved because the columns are going to be sparse.
Okay, so let me put in this way. So it's basically, if you're traditional RDBMS, you create a one table example, and whatever the rows which can have a different kind of a column. So you can say that the table structure is the table name and column name and the value. So each row a row ID. Okay. So each row have column name and the value pair, name value pair is coming down, and this name value pair can depends on the row ID. It can go either 10 columns or 5 columns or 4 columns. It's basically we are restricting instead of going into a column, so it go into a rows which maintain as name value pair, like XML kind of a way is represent in a rows. Okay, I got it.
Correct. That's correct. That is exactly what you're saying. Okay.
Yeah. Thank you.
So let me go back to the Kumar stuff. Okay. For NoSQL DB, also we need to store as key value pair. Yes. So this is the same example here. In an RDBMS, the column names are defined upfront. Okay. And it is not stored with the data. Okay. Because it's stored in the catalog, system catalog, where which column is what type and other attributes. Correct. The RDBMS only enforces once the data comes in that the data type is of this type, and we have all these columns available. Otherwise, it will put blank or null basically. Correct. So that's what the RDBMS does. That the structure of the table is defined. In the case of NoSQL, the structure of the table is not defined. Only the placeholder of the table is defined. That we say that we have a table called user. So we are saying we have a table called user, but I don't know what is going to be stored inside user. That I will decide when the data comes. If user name and user address is there, okay, I will add 2 columns inside that and add the data. But tomorrow if there is 10 fields which is coming for the user, I will add that column and put the data. So that is the way the schema, the data is stored, and that makes it flexible schema. Okay. Any other question? Hello? Any others?
So I'm bringing another question. Is it this one is like the transaction is as begin transaction and the end transaction kind of thing is there, or it is not there in the Cassandra?
Yeah, so those are the features which we are talking about. So to answer it, yes, if you want begin and end transaction, you have to write it your own. There is no by default begin and trans, because every operation will have at a row level only. Okay, there is no cross row updates or inserts which will happen. It will always row by row insert, row by row updates. Okay, All
So
which will happen is multi-rows is only used when you are querying. You can only query across the rows, range queries.
okay, so one row, one at a time, and one table, one column, whatever it is. So if the multiple tables needs to be updated at the same transaction level, so it's not possible, you are saying.
Yeah, so yeah, and then let's get there. So I don't want to jump into all that right now. So right now the only thing which I have covered, and Tapan is also mentioning, let's go step by step. So the whole idea is this: what I wanted to cover till now was only these key messages. That what are the problems for RDBMS? We need to understand that RDBMS, as the volume increases, there are problems. RDBMS has problems with the schema part of it, because the usage pattern of the new applications are different. They are write once and read many times. They don't need ACID. They are going exponentially large. So, and they don't really need complex joins as well. If you look at the usage pattern and the usage of these applications, they need to store complex data structures into the data. And they don't know upfront what is the schema which they have to model when the data and when what data will come. So these are the challenges which are there, and RDBMS can try to address that problem. But once you address the problem in RDBMS, two things which will be definitely a problem. One is the cost is going to go exponentially high, okay, and guaranteeing ACID in as the database starts horizontally scaling becomes a problem. So vertical scaling is the only option for RDBMS. This is what I want to emphasize till now. So I hope you guys have got that part and say that, yeah, this is the new world of data and these are the challenges and why NoSQL is really required. So the whole idea which I wanted to do is just get these fundamentals right. We will go from here. Okay, so now we will go to Cassandra and details and all of those separately. So look at this picture, and this will summarize what I am trying to. One second. I think something happened here. Okay, screen is now shared, correct? Okay. So here is the thing. What we are saying is, don't assume that RDBMS is going to go away. So there won't be Oracle DBS today here and they will say, okay, my job is gone because NoSQL is coming. Okay, no, it is not the case. The only thing which we are saying is, there is another set of applications which are emerging. And with the advent of big data, these applications are the analytic applications, and the demand for these applications are increasing. Okay, so we need to use the right tool for the right set. So that is what it is. Okay, so RDBMS, the whole idea is, you might, when you need a cycle, you need to have a cycle. When you need a bike, you need to have a bike. Or when you need a Ferrari, you need a Ferrari. So that's the idea. So when we look at it, we are saying that it is not about that RDBMS is going to go away. RDBMS is still required because there are many applications which we have traditionally worked with, and all of them needs ACID, and hence RDBMS is here to stay. But what has happened is, there is a huge set of new applications which are coming in, and for them the need of the usage or the usage needs are different, the scale on which the data has to be stored are different, the flexibility needed on the schema are different, and that's where the NoSQL starts off. And again, there is no single NoSQL, there is a large various NoSQLs are there, and the whole idea is how these NoSQLs has to be brought into together. So now let's go to the next one. So what does NoSQL really stand for? So NoSQL means not only SQL. So it means there is something beyond SQL also which is there. So don't go with the name. There is no very hidden meaning inside that name. NoSQL stands for not only SQL. That's the only definition which we have. It doesn't store relational structure. So we need to give away the third normal form of relational storage, and we no more store data in a relational form, which essentially means relationships are not explicitly defined in the database. Relationships are handled by the application. So what means is, if you have, let's say, user and user address as two different tables, okay, there will be no key which will link user and user details directly and by the database, but your application should know that the user ID in this table is equal to the user ID in the other table, and I'm going to use this when I want a relationship to be established. So that is what it means. It means that database is not going to enforce your referential integrity constraints or relationships, and that responsibility now shifts with the user. Second thing is, we talked about that it needs a flexible schema, and most of these things are all flexible schema. The schema where the fields can evolve as it goes through, and there is no concept of joins in any of these NoSQL. The join part is gone away. Okay, so the join, once you want to join, you need to pretty much get into the MapReduce model, and we'll come back to that. How do we do joins? Okay, but by default database will not support joins. That is what it will be. You will have to, the application programmer has to do the join. That is what it is. So the responsibility is shifting from database to the application developer. And there is no ACID. It is a relaxed ACID, which is basically available, soft state, and eventually consistent. So it can handle large volume of data. So these are the key thing which you need to remember about NoSQL. That there is no join. You might not get ACID. Okay, it will give you flexible schema, and it can handle large volume of data. Any questions? So assuming there is no question, I am going to go ahead. Yeah, so Tapan is asking, yes, developer has to take care of join. Yes, that is the correct answer. When you want to join, see, first of all, join should not be there to a large degree, because the data will be kept normalized, and you will replicate the data in different forms. So the need for join will be hardly there. But yes, if it exists, it has to be handled by the developer by taking the data from one table and then using the keys manually, going to the other table and get whatever he wants. So that will be done in the programming side. It is not done at the database side. Okay. So we move on. So next what I want to cover is what are the different types of NoSQL databases. Okay. So if you look at it, there are a lot of categories of databases. So first, fundamentally, we categorize the NoSQL databases into 4 different high-level categories. It is not like that is the only 4 categories. Okay, if you go to nosql.org, there are thousands of databases listed, and each has different characteristics and everything. But from a usage perspective and the popularity and the relevance perspective, these are the 4 different types of NoSQL database. The first one is called the key value store. Okay. Now the second one is a column store, third is document store, and the fourth is a graph store. Now we'll go to each one of it and understand what a key value store is, what is a column store, what is a document store, and a graph store. Okay. So to understand a key value store, we need to know if any of you guys have worked with Memcache. That's a very excellent example. Or if you have not worked in any of those, let's start with understanding a website application, a small website. Okay. So for a website, when a user logs in, what we do, we put every data in the session and the cookie. correct? So that when the user comes next time, we can pull that information back and show that user data to the user and give him a contextual saying that, yeah, you visited these links, you have done this, and we can tailor the interaction, or we can personalize the interaction of that user on the website. So that is the typical requirement. And what we traditionally do, we create one user table, user session table, and store all the session details of the user into that particular one. Okay. Now imagine that there is millions of such users visiting your website, which means that you need to constantly, as the user logs in, you have to go to a table with that user and get the whole string, whatever is the session related information, and then give and do some processing with that. And this, when you do it very clearly, you feel that the database structures are becoming bigger and bigger problematic. So what you do, you add the caching layer on top of it. And in the cache, what you will do, you will say, I will always query the cache with the user ID. And when I go with the user ID, I should get the entire session. You don't store details of the details inside the session, because I will parse it. I will know what is inside the session. I will take care of it. All you do is just take that whole data of the session and store it as one contiguous bytes into the cache. All I'm going to do is I'm going to go with the user ID and get that whole entire byte of data. That is what you will do. Clear? Now once you get that, if you have to work with Java or any other serialization, you will take that whole contiguous byte of data and map it back to an object. And once it maps it to the object, you will get all the data, all the fields split properly for that particular user. Correct? So the requirement is to store a contiguous byte of data against a particular user ID. So that is what a key value store would do it. Even in an application, if you want to store some data based on a particular key, you will use a key value store and put it into a hash table, hash collection. Correct? So in a map, you will put it in a map. You will put the key, and for that key, what is the value, you will put it and keep on dumping into the map. The only disadvantage of a key value is that you only can query by key. You cannot query by any attributes of the value, because there is no attributes of value. There is only one value, and it is a contiguous bytes or array of bytes. Correct? So that is the key value fair. So now it is not like reading a file. Tapan was asking, like, yeah, is it like reading a file? No, it is not reading like a file, because when you are reading a file, you are reading from top to bottom of a file. Correct? You are reading sequentially, or you will do a random access on a file. If you are doing a random access, you are using the file pointer. Correct? That also is not a it is always based on an offset. So you know that, yeah, from the file start of the file pointer to the this point, this much is the offset. But in a key value pair, you never know. Okay, you always know that this is the key and I want the value. So you are storing like a key value pair. It's like a hash. So you give the key and say, or you can look it as a locker for now. The best, whoever has not been into this key value pair business earlier, I would say that, look, imagine it as a locker. You open the locker with a key. So there are so many lockers available. So you know which key is come. So you know which is the locker. You open it and you get the data from that locker. Simple. So it's a key value pair. But you don't know, you cannot query inside the locker from sitting it outside. Correct? You only can query based on the key. So you imagine a bank locker. There are many keys available, and the many lockers, and each locker is only available through a key. So you can access the data only through the key. You cannot go inside and say, get me all the key lockers which has gold stored in it. You cannot do that. Okay? Because you don't know you don't have access to data inside it. That is the reason. Okay, so that's a key value store. A key value store is a distributed hash table. The only way you can query the key value store is using a key. And all you store is a contiguous array of bytes inside it. Now that array of bytes will have a structure inside it and all of those, but you cannot query it. You can only store key and value. Now what is an example of a key value store? Memcache is one good example if you look at it. DynamoDB is another good example where you store only key and you only get values. Okay. Berkeley also is the same. Here you go, put a key and you get a value. So these are all key value store. The only operation they support is get and put, and maybe a delete the key. That's the three operations which it supports. You say get the data for this particular key, put the data for this key, or delete this key. That's it. So every operation goes through the key. There is no other way you can access the value. Is that clear? The key value store. Okay, so I think we will move ahead. It is very clear that the only access mechanism for a key value store. So the biggest limitation for a key value store is you cannot query by the data inside the value. Okay, so data values are always like a black box to you. All you can do is you can query by key. So the data, now whether the data lies in memory, that's what Arun is asking, is the data in memory or not. It depends upon how the NoSQL stores the data. Some NoSQL might store the data in the file disk, or some might store in the memory. It is immaterial. What we are saying is you need to imagine this key value store is a NoSQL database which supports three interfaces: get, put, delete. So it's like a black box to you. You tell the system that store this key and the value is this. You put it inside. So that is put. Now when you want to query, you can say get me that particular key. So if you lost your key, your data is gone. Okay, you cannot get the data from a key value store if your key is gone. Because if you start iterating, that whole key iteration will take a long time and it will be a mess. So usually they don't support iterating across key. So how does it get used? The usage is always that you create an intelligent key like the session ID, user ID underscore maybe date or user ID underscore something. So that becomes your key which you can dynamically construct. Okay. So seeing your data, you can dynamically construct a key, and so you don't need to remember the key. That is the way the key is being used. Okay. Otherwise, if you are hard coding the key, nobody will be able to get it, because then you have to maintain a list of all the keys which you have stored and what it has been stored, which essentially means you are having a database outside. But the biggest usage of this key value store is because the key can be dynamically constructed, and the keys which are dynamically constructed are the only keys which is used. The values cannot be queried. That is what the key value store is. An example is DynamoDB and others. And we have that chart separately, so don't need to worry about. I have the slide for that. Now comes to the column store. So in a column store, what you need to do is you need to expand that key value store a little bit further. That is what your column store will happen. What you have done in that is access is still by the key. Okay. The only thing is now the value is made queryable, in the sense there is some structure assigned to the value. So that is what, going one step from the key value store, you comes to the column store, where the value is now stored in a column family. Okay. So the value is now stored in a column family, which essentially means each values is now grouped into certain groups, sections, and we can store multiple of those sections. And that structure we will see once we start seeing Cassandra. So the example is Cassandra, Edge base, or column family database. Big table from Google was a column family database. Okay, so these are the examples for column family database, and we will look into column family database in more detail. So don't worry. So the only thing which you need to know is in key value store you cannot query the value, but in column store that value is also exposed. So it is a locker with a mirror kind of a glass doors for a locker. So you can see the inside of the keys. So you have the key also, but you can peep inside also without actually accessing the data. So that is what it is. It's like a locker with the glass. You can see a bit inside. Once you open the key, the data is little transparent. Okay. Now what is document store? Document store is like a store which will store the entire JSON, where you don't really need to worry about the what is the attributes and column families and all. The value is nothing but a JSON file. Okay, so let me explain you how it works. So let's say you have an XML or a JSON and you want to store it. So you know that there is for this JSON, this is the key. So you put the key and you put the JSON directly. Similarly, you put the key and the XML directly. So that entire XML is stored or the entire JSON is stored, and you can query now very flexibility inside JSON. So that is the advantage you get there. That in the column family store the querying is still limited, but once you go to the document store, the entire querying becomes very clear because the structure is very clear. JSON structure is very clear and we know how the JSON structure is, and so querying a JSON is easy, or querying a XML is easy, like the XPath queries which we write, correct? So those are what the techniques used for document store, but still it is key and a document. Yes, so I saw some message from Shravan. It's like key file structure. Yes, so you have a key and the key, the value is nothing but a JSON. Okay, that is what it is. The value is either an XML or a JSON. So you could see that from key value store to column store to document store, what we are changing is the value. The value in the key value store, nothing is transparent. It's a black box. In the column store, the value is stored as the columns, okay, column families, and in a document store, the value is stored as a JSON document. And the same thing happens here now in a graph database. The graph database is not a key value pair based database. It is a proper graph. It stores a proper structure. Okay. So the graph is like, it will have a node and it will have properties between the nodes, and it will have node properties also. It is just like any other graph. If you have looked at computer science graph data structure, a data structure of a graph is now stored inside a database. That is what it is. So that is a little complicated one. So graph database, there is one popular graph database called Neo4j, and there is one hypergraph. There is another database. So let's look at in detail all the available graph database and other things. So this is the picture. You have a key value stored. These many are the key value stores which is there. You have a columnar store, Edge base, Cassandra, Hypertable, Google table, Big table are the columnar databases. Document store, MongoDB falls under that. Then you have a CouchDB. The CouchDB supports XML also, and then you have a SimpleDB. SimpleDB is from Amazon. Then you have GraphDB, we have Neo4j there, and Infinity Graph. The key thing is each one has its own thing. So here it is the value is not accessible. Yeah, so I think I'll come back to some questions soon. So first let's finish this. So you have key value, columnar, document store, and graph, and these are the examples. Okay. So the whole idea is that in this the value is not accessible. In this the columns are somewhat accessible. Document store, the JSON and XMLs are fully queryable, and in graph the whole data is stored in a graphical structure. The only thing which is common amongst all of them is they are all highly scalable, they are all fault tolerant, they are all distributed databases. They don't support joins, and they have flexible schema, so that you don't need to define the schema upfront. So this is all about the NoSQL landscape. So let's go back to questions. See, column store and columnar database. Okay, so there is a slight difference. It is more at the storage mechanism. The column store is inherently saying it's a modeling technique. Okay, columnar database is a storage option. So that's what Rakesh's question is all about. We will cover that out once we get into the little bit more detail on the data modeling aspect of it. What's a columnar storage versus a column store database? Columnar storage you can do it on any place. Anything which you can, even in RDBMS you can store it as columnar. That is what HANA does basically. But column store is a column family store which also can be stored in a columnar format. So we'll come back to that. So one more question Shravan has asked, document store, is it not similar to storing on HDFS? No, document store is not like storing in HDFS. Storing in HDFS is a raw file. Okay, you are not altering anything, you are just storing the file as is. And in HDFS you cannot query it directly unless you use Hive, and Hive parses the file and queries it, correct? While in this case of columnar or the document store, once you load the JSON is understood by the, so it actually validates the JSON. Okay, in HDFS that validation doesn't exist. It is just a file, and when the querying, if it fails, it fails. But in this case, if you are trying to store a JSON in a document store, it will validate that particular document and say that yeah, it is compliant to JSON, and the moment it stores, it is fully queryable. So there is a huge difference in storing a document in HDFS and a document store per se. So any questions? You can speak if anybody has any questions. Okay, so there is a question, where does HANA fall in? Okay, so HANA is not a relational NoSQL database. Okay, it doesn't support flexible schema. It is a relational database. Is that clear? HANA is not
Is it relational? Is it a relational and columnar like that?
Yeah, so what happens in HANA is that, see, if you look at an RDBMS, a traditional Oracle database, okay, so the Oracle database, the data is stored in a disk. The data is stored in a row-oriented format, not column-oriented format, okay. So what HANA does is takes that same Oracle database and say that I will store the data in memory, okay, but I will support ACID because I am going to store relational. So it is not a NoSQL. What it says is, now since the access on the data can be made faster in some cases using a columnar storage, instead of storing in a row oriented form, the same relational store I will store in a column oriented form. So the entire column is stored together. Okay, so that is what you can do. And when you define the table in HANA, you can define whether it's a row oriented storage or a column oriented storage. So HANA is not a NoSQL database because it doesn't support flexible schema. Okay, it is just an in-memory kind of a thing. Okay, yeah, and Ravi is saying that yeah, this is something like quick view. Yeah, to some level I would say, but yeah, it is more than quick view. Quick view is only for reporting and storing that, and then they do something. Yeah, they are also going towards the HANA view, the click view guys.
Is it more like Teradata?
Yeah, so if you look at it, see, if you put Teradata in memory, then you can say that yeah, it is close to HANA. Okay, so it's the HANA principle is more about moving it into memory. Instead of using disk for storage, use memory for all the operation. Okay, and only failure point you will store into disk. That is the only change in HANA fundamentally. Yeah, entire data is in memory. That's it. So that means you need terabytes of things. So there is another guy who is coming in between. Now you should know about Terracotta. There is a company which has acquired Terracotta and they are trying to come with that. So same guys. So same concept. Both Germans only. They are trying their best on that. So in memory, you will get soon one more database coming on the way. Yeah. So that Terracotta is, yeah, that was an open source. Somebody has taken it and now they are building some things. I recently saw some articles around that. Okay, so moving on, let's get into the next level. Understand the key character. Now this is more at summarizing. I think we covered almost everything. It's more about summarizing, understanding the characteristics of NoSQL. And so now tomorrow if somebody asks like, okay, what is this a NoSQL? The immediate question you need to ask is it supporting flexible schema? Is it highly available? Is it a distributed database? Okay. So the moment you answer the 3 or 4 questions, you will immediately say that yeah, whether it's a NoSQL or whether it's a relational. So in this case of HANA, obviously the answer is very clear. It is a relational database. It's not a NoSQL database. So the key aspect characteristics of NoSQL is that it will be highly available, and many systems can be made highly available. HANA is also highly available. Okay, so highly availability is not the thing, but highly availability at low cost is a big thing. So that's what it is. You can scale elastically, which essentially means you can add new nodes and scale it, which makes it more flexible. The schema is flexible. We talked about the sparse storage, and it is semi-structured. Obviously, it's not fully structured, it is semi-structured. The limitation we also know, it supports very limited query capability because the joins are not very powerful. Then eventual consistency is what it supports. Okay, so that is one thing. Then you are looking at, there is no standardization in this space. The SQLs are still evolving. So those are certain things you will see it. Then the next thing is access control is a little bit of problem, and that I think yesterday also we discussed that there is not too much access control mechanism in these NoSQL databases. I tried to draw it in a different form.
I'm sorry. If you go back, there was one more point. The portability might be an issue. So it's pretty much like, you know, if you are stuck with, you know, some structure of NoSQL, whether you use Pig, Hive, or you know, Cassandra, it's hard to migrate away from it. Is that what it means?
See, it's not a straightforward migration because there is no tool which gives you a migration from Cassandra to HBase. Okay, but it doesn't mean that it is not possible because the data is stored. The key problem which comes with migrating of a NoSQL is that you don't know the data, correct? Because anything and everything can be stored inside NoSQL. So imagine our same example of users which we try to store, and all the users which we gathered from the social sites and their attributes. Now when you try to migrate, what would happen? You don't know, you don't have a head and tail of what is stored inside this. Because once you now you have to migrate to HBase, you need to know, okay, what I'm going to model, how I'm going to model, how I'm going to pull this data, how I'm going to push it there. So that becomes a little bit of a issue. So that is where the portability across different NoSQL becomes a bit of a issue. So when before you choose, you have to choose the right one. That is what we would say. But in case of a document store, it is not that case. The column family is where the mess starts. Key value store is still okay because you can always move a key value store to something else, because now the only thing you will move away from key value store is by splitting the values and moving into either column store or graph store or document store. Document store is also very easy. I don't think there is any portability big issues on document store, but column family is little tricky and messy. Okay.
So in the same vertical line though, is it not that difficult to migrate, for example, HBase to Cassandra to all the columns?
It's not that difficult. It's still easier to migrate between HBase to Cassandra. But if you say from Cassandra to MongoDB, if you have to migrate, it becomes difficult.
Got it. Thanks.
And it's not like it is impossible. You need to just, based on your application specific, you can do it. You don't have to write a program which will do that.
And I think more importantly, these technologies are not matured yet, so there is no third-party tools developed for migration for the stuff.
Correct, and there is not too many migrations happening as well. So these will evolve once the people start migrating and standardizing on one few of these things. Correct. So right now, the people do a good evaluation, and then they'll settle on their particular need and requirement. So they don't migrate unless like DataStax goes bankrupt and said that okay, I'm not supporting Cassandra anymore. Then people will start doing that. Similarly, for HBase, if there is no community support, then people will say, okay, let me go to DataStax at least and do Cassandra. So that is going to be the only driver. So coming back to the key characteristics, I try to put this again one more time in a different form so that you understand it. Flexible schema, highly scalable, easy to configure, eventually consistent, and cost effective. These are the characteristics we should look for when you are looking for a NoSQL database. And the way how much size and complexity you get into is the for different data store is what I have shown here. So key values are pretty much the simplest. So you can go very large size with key value pair. With column family, the size, the complexity increases as the size increases. Document database, again the same thing because the querying and other things are supported. Graph is the most complex of all. Okay. So now the big one which I want to cover was the CAP theorem. I'm not sure whether you guys are all okay to continue for some time, or anybody has a stop where we need to stop in some time, because now there is one fundamental thing and I want to cover which is CAP theorem, and then maybe we can break from there, and then we'll continue from beyond that in the next session. So that's what I intend to do. So okay. So I think we'll take another half an hour to close this, and then we move on. So moving on, CAP theorem. Mr. Eric Brewer has actually put this theorem forward. But before we get into this theorem, I want to introduce three concepts: consistency, availability, and partition tolerance. And then once you understand these three concepts, all the theorem says is you can get only 2 at a time. You cannot get 3 at a time in a distributed system. That's what the theorem clearly says. So the whole idea is about understanding consistency, availability, and partition tolerance. Once you understand this, all the theorem is saying is you cannot get all the 3 at the same time in a distributed system. You can get only 2 at a time. So all these NoSQL databases take, because they are all distributed, they look at the CAP theorem and say that I will support availability and consistency, or I will support availability and partition tolerance, or I will say consistency and availability. So these kind of permutation combination, they said I will claim to support, and others we will not support. So that is what the whole idea is. So let's go and understand what is consistency. So basically consistency and availability is very easy. Partition tolerance is where the mess starts. So consistency is like, yeah, I write a data in one node, and since it's a distributed system and which is obviously going to be replicated, so whatever I wrote in one machine has to get replicated to its replica in some other node. In between, if the client asks for that same data, now that request can go to the node which I wrote the data, or the request can go to the replica where the data has not really reached. So what should the database do? One way is the database could say, okay, it is not ready yet, I am not going to give you any data. Okay. If that is what the database does, then it is consistent, because it is not giving any stale data to anybody till, and it is only giving a consistent view of the data. On the other hand, if the database says, okay, don't hold me for this, but this is the data which is available now, take it, come back and check at me later, I will give you, if there is a change in data, I will give you, but I don't guarantee consistency. Okay. So I hope consistency is clear to you. If not, please let me know. So I have one more slide which talks about consistency. So consistency means that if somebody writes a value to a database, other users will get that value immediately, and it will get the same value irrespective of where he queries the data from. Okay, so that is consistency. Any doubt? I think we need to clear one by one each of these. So I want each of you to look at it and say that yeah, it is fine. So if it is consistency is okay, I will move on to the availability. Okay, so I see somebody saying it's good. Okay, fine. So consistency means everybody understood. So let me go to the availability. So we are again talking about a distributed database, which means when you look at a distributed database, there are different nodes of database. Okay, and the data is distributed in many of these nodes, which essentially means if one of the node goes down, what will be the database say? Will the database say I am not available? Or with the data, if one of the node goes down, database will still be available. So that is the concern of availability. If the database says if one node goes down, I cannot service it, that means the database is not available, and it is pretty much trying to ensure consistency at the cost of availability. On the other hand, if it says that yeah, if my one of the node goes down, I am going to redirect the request to another node, and that node is going to respond to the data, which essentially means that the database is trying to be as much available as it is feasible. Okay, it's trying to redirect the request to the available partition or the available replica. So that is what availability means. Availability means if some nodes fail, the distributed system can redirect to a different data location in some other node and still make the system available. Okay. So I hope consistency and availability is clear. This is very simple. Okay. Now tolerance to partition is the catch. First we need to understand what are partitions, and then we need to look what is tolerance to partition. So to begin with, first let's understand the network topology. So from a network topology, let's assume you have two data center. Okay. So we start with, let's say, a New York data center and a San Jose data center. There are two data centers. In New York data center, there are 5 nodes, and each of the nodes forms a distributed database. And as a part of this distributed database, there is another 5 nodes sitting in the San Jose cluster. Okay, and they are connected through a WAN link. And this whole 10 machines form a single distributed database. So we are talking about a single distributed database of 10 nodes which is replicated in San Jose and New York. The reason why I called it San Jose and New York and not a 2 data center inside the same premises, it can be the same. Okay, but I just want to make sure you are clear on that it can be geographically distributed also. It can be physically distributed in the same data center. It can be geographically distributed as well. Okay, so think about it. Give me 1 second, I'll be just back. Hello. So now we are talking about that we have a distributed database with 5 nodes in one place and 5 nodes in the other place. Now when a node from New York, let's say there is a client in New York which wants to access the database. So the client is trying to insert some data into the database. So what happens? The client inserts into New York data center. The data gets replicated into the San Jose data center, and any client comes in San Jose, he'll see the same data. So the database is functioning properly, the system is available. Now when we try to give an availability constraint, so let's say one of the node in the New York data center is down, and the client has inserted some data and he wants to get the data from New York, but the data is not available. So it goes to San Jose, gets the data and gives it to the client, because it's a seamless distributed data system. Similarly, it works in the other way also, that any client in San Jose, if he wants, it will go to across the cluster, get the number and get it. So the replica and everything is working fine. So what is partition tolerance? Partition tolerance is the mechanism where, let's say, the connectivity between New York and San Jose goes down. Okay, if New York and connect, so the group becomes 2 groups now. Okay, because of the physical connectivity going down between San Jose and New York, the whole 2 clusters become 2 independent clusters. So now any client comes in New York, since the data is always local, he assumes that yeah, everything is good and he gives response to the data. But somebody has updated that data from San Jose. Now from San Jose to New York, the data is not come because the network is down and that cluster is still behaving properly and it is replicating locally and keeping it. It is assuming that once the cluster comes up, I am going to replicate it. So this is what is partition now. Now when a partition happens, the network is now split into 2 groups. Each group is acting independently. Now, what is tolerance to partition? Tolerance to partition is how does the system behaves under such kind of a partition. So, scenario number 1 will be, once the partition happens, both New York and San Jose will say, boss, we are down. We cannot operate anymore because our buddies are down. The network is down. So that is one operation. In that case, what we are trying to ensure? We are trying to ensure consistency for the things. But we are not going to give you availability, and we are saying we are now partition tolerant, because even under a partition situation, I am able to guarantee consistency. Okay. But the problem is, with that, the network will be down, the database is down. Okay. Now, consider the other situation. Other situation you say is that even if the network is partitioned, I will continue to operate and I will continue to serve the request under the assumption that I am not consistent. So I will tell the customers that, boss, I am not guaranteeing consistency, but I will give you the response. Okay. And when the network comes up, I will sync up and make it eventually consistent. So that is the model. So there are two things which can be done. One, the partitions can be said that, okay, I am not tolerant to partition. Okay. So the moment partition goes on, I am going to just shut it down, and I am going to guarantee you consistency, and I am going to be tolerant to partition. The other one is, I will say I am not tolerant to partitions, but I will not then guarantee consistency. So this is the key thing. So you have consistency, availability, and partition tolerance. What CAP theorem says is you can optimize your system for 2 of them, but never for all the 3 in a distributed system. Is that clear? Can a database be distributed across multiple clusters, 5 nodes in one cluster? Yes, that is correct. In fact, Cassandra will support that. Okay. So nothing is preventing us from, oh, something has happened here. 1 second. What is this? Okay. So any questions? Now people can speak up if there is anything required. So I want everybody to understand this CAP theorem. What CAP theorem says is, the partition tolerance is something which is very important to understand. Other than that, consistency, availability, everybody is clear. So it's not a big deal. But partition tolerance is something, it's the network partition which we are talking about. It is nothing else. So network, when the network, the partition, one of the partition goes away, then it becomes a group of clusters, and each clusters now start operating independently, and we get a situation like the split brain situation. And in that case, how the system will operate is the question, and how the database is going to be designed in that system is what it will make it. Yeah, so that is the next question to answer. So I'm going to put up the next slide, which will show how each of this CAP theorem is going to get looked at. Is it clear to see? So if you see here, this is the guide for where the NoSQL system looks at. So we have given relational databases also here, key value store, core room oriented, document oriented. Graph is not put it, so don't worry about graphs. These are the 3 important now: key, column, and document. And we are trying to say which falls where. So if you see Cassandra is guaranteeing availability and partition tolerance, okay, at the cost of consistency. So Cassandra, SimpleDB, CouchDB, Rec, Dynamo, Voldemort, everybody is looking at availability and partition tolerance as their fundamental thing. Cassandra has one unique thing which says that it's tunable consistency, which essentially means you can make Cassandra to work with C and A also and compromise on P. Similarly, so the consistency in Cassandra is tunable, and we will see how that can be tunable in the subsequent discussion. Okay, but fundamentally it has been built between availability and partition tolerance at the cost of consistency, and saying that we will get eventual consistency. On the other hand, edge base compromises availability to ensure consistency and partition tolerance. So that is where the fundamental difference comes in. Okay. Big table, hyper table, all of this column family shows. So in the column family databases, only Cassandra is the one which will give the availability and partition tolerance. Similarly, in the document store, you see that SimpleDB, CouchDB, React and all will fall here, but MongoDB is in the consistency and partition tolerance thing at the cost of availability. Now, similarly in the key value store, you have Berkeley, Memcache and others showing consistency and partition availability at the cost of availability. While people who have worked on relational databases can see that relational database is having consistency and availability at the cost of partition tolerance. It is not going to be partition tolerant. I hope this is very clear. So this is fundamentals. So this picture you need to remember that this is CAP theorem from Rivers-Eric's CAP theorem. All it does is it says you can only pick 2, and all these databases have picked 2. You should remember that relational databases fall in the availability and consistency thing. It is guaranteeing availability and consistency, but immediately the partition happens, it will just shut down. On the other hand, Cassandra will not shut down when partition happens. It will give up the consistency. Okay. Similarly, if you look at edge base, it will give up availability when a partition tolerance happens. Clear? But it will still try to give you a consistency. And this is the choice which you need to make based on your application needs, whether availability and partition tolerance is your most important requirement, then you go for Cassandra. On the other hand, if you look at consistency and partition, then you will really go with edge base. So Shravan says, if you want to look at a clickstream analysis, which database would you go for, or which would be your thing? Now, when you are looking at a clickstream analysis, now it depends upon what is your the topology of your site. So if your site is multi-geographical, distributed across the world, and you want to have a single system which does clickstream analysis for that entire site, okay, which is geographically distributed across the place, that is where you would say availability and partition tolerance is very important to me, and Cassandra is a choice. On the other hand, if you say I am not geographically distributed, I am only locally distributed, I am still okay, part of it, but I want consistency. And in a clickstream analysis, I don't know whether consistency is that big of a deal. Okay, if consistency is a big of a deal, then yeah, you will go with edge base. But eventually, I would say eventual consistency is a good enough case for a clickstream analysis, and hence, if the sites are largely distributed geographically, and not only geographically, I am saying that yeah, it is very, very large, then you would go for Cassandra. Otherwise, you would still settle for edge base. So that's the choice you will make. Oh yeah, so Ravi has made a good observation, saying that anything within availability and partition tolerance And these are all dynamo derivatives, and which is correct because any of these are peer-to-peer networks. When you need an availability and partition tolerance to be guaranteed, you need to have a peer-to-peer network. And most of these, I think, are I don't know about React and others, but most of these Dynamo, Cassandra, Simple, Couch, all of them form a peer-to-peer network. So a peer-to-peer topology is in this segment. Okay. So there is one question from Kumar: why importance given to partition tolerance these days? Yes, partition tolerance is given importance these days because the sites are becoming geographically distributed, the size is becoming larger, the volumes are huge, and hence a single rack or a single data center is not able to host all the data which is required, which essentially means we need now a geographically distributed connectivity, okay, and which during that time is where partition tolerance comes in. So in traditionally what we used to do in RDBMS is we used to do offline replica. So let's say there is a site which is locally in one data center. We use the replication service to service and the other locations. We don't do a online replication which is very dynamic. It is always a replication service which runs and the data is replicated across the cluster in thing. So that is the model which we have used. We have not used a distributed database which spans across different databases earlier, because RDBMS focused on consistency and availability. If you focus on partition tolerance, then this will be not guaranteed. So people have already quietly focused on here, and to guarantee that it will move across the data center, they use replication solutions. That is what they have done earlier. Yes, so all this is all RDBMS in A and C. Okay. A and C is the only place where RDBMS supports. All OLTP applications earlier, yes, A and C is the game. Partition tolerance was never looked at. So I hope this completes your CAP theorem, and you are aware of that. And any questions further, let me know. But this is a good logical point now, because I don't want to cover too many things today and make you confused. So let's summarize what we covered today, and we'll stop it at this point, because this is a very logical point for covering NoSQL. So from an agenda perspective, let me look at the course content. Yes, so this is basically what we have covered till now. Relational versus NoSQL, type of NoSQL, NoSQL landscape, CAP theorem, and eventual consistency. So eventual consistency will cover in detail further as well once Cassandra comes in. So eventual consistency really means that after some time the consistency will get achieved, and then when you look at Cassandra, let's look at it in more detail and see how eventual consistency will come through. The second part is the key characteristics of NoSQL database. We talked about acid versus base. Okay, so basically available and eventually consistent. Soft state. So that's a part which we covered right now. And any questions, let me know. We'll pretty much stop here.
Hi Sudesh, this is Shravan.
Yeah.
I just have the question on that graph database, the graph store. So yeah. By any chance Facebook is using that graph store? Because I know Facebook is using Cassandra, but the new feature, whatever we are seeing in Facebook, which is doing that graph search, is it using the graph search kind of NoSQL database, or is it done by Cassandra itself?
See, it is not done by Cassandra, that much I can tell you for sure. Okay. Okay. Because a graph kind of search, the graph API which they support search right now, that kind of a search and that kind of a speed which they are looking at will not really come out from a a Cassandra kind of a model at this model, because the relationship is what we are trying to search, correct? Once you start trying this relationship, you need a real graph thing. Okay, but what they have done is they have tried to write a wrapper is what I'm thinking right now, because the distributed graph databases are not still in mainstream. So they are still using some graph databases, but I have not got that detail, or they have not published that detail to anybody, that how they are supporting the graph, because that's their powerful feature right now. So when we have actually supported customers for that kind of a query, we have used the graph database. Okay. So when we used the graph database and we have supported queries like that. But I cannot comment whether Facebook is definitely using Neo4j or Giraffe or some of the graph thing. But there's a lot of research happening, and once they make it public is where we will know whether they are really using graph database behind it. But I'm sure that they are not using Neo4j for sure. So
okay.
Yeah.
And how big of a deal is to migrate from HBase cluster to a Cassandra cluster? Is it like, I mean, I know this maybe eventually you're covering up these kind of things, but at high level, like a yes or no kind of thing, you can say, how big of a deal it is? Is it something like just use a scoop or some extracting tool to extract it from a HBase nodes and load it onto Cassandra nodes cluster, or is it bigger than that actually?
See, the data will move, because the format in which the data is stored in both HBase and Cassandra, the form, the column family, and the structure is same. Okay, but the interfacing is not same. So you will need to get the data out of HBase, and then you need to push it to Cassandra. Now the only thing which you need to is that the column family definition, the way you define the column families in HBase is different than the way you model it in Cassandra is different. So there would be more of architectural decisions on the column families and other things which you need to do. But once that part is done, the data movement is not that complicated.
Okay.
Because the structure is same. The data model which they use, both are same. Okay, there is small changes here and there, but it's not that big of a deal that you will find that kind of a difficulty. Okay? And but the organization of the data, the design will change definitely.
Yeah, and HBase will share the HDFS nodes, but the Cassandra will not share the HDFS nodes cluster. Correct?
It will not share. It will not share.
Thank you. That's all I have. Yeah.
Yeah. Because the advantage of HBase that way is that you can write a MapReduce program on the HDFS itself, while as it queries, so that there can be interaction between HBase and HDFS. While here the interaction will be HDFS and Cassandra file system.
Are we going to cover more on this last thing that you just talked about with respect to HDFS, comparing HBase and Cassandra? I didn't get that completely.
See, what I intend to do was at the end of the course, then once you know Cassandra in detail, that is where the comparison would make more simple and more meaningful. Right now it's all the theoretical comparison saying that the column family structure is the same in Cassandra and HBase. Okay, but the way the data is stored, like there is a region server in HBase versus in Cassandra, it's just pretty much the tokens. Okay, so there is a simplistic way of storing data in Cassandra versus how the data is stored in HBase. So unless you know how the data is stored in Cassandra, those kind of comparisons will not make sense. So that is where I am not attempting to do that right now. I will do that once as we go through, when we are looking at a specific chapter in Cassandra and we say that yeah, this is what Cassandra is storing, then we can contradict and say, oh yeah, no, this is not how HBase is storing, this is how HBase is storing. Okay?
Okay, thanks.
We can go it that way. Yeah, Arun, this session is recorded and that will be available. Okay, you can contact Divakar for that. So anything else? I think we can stop here. It covered initially thought it was a 1 hour part, but yeah, it covers the fundamentals at least. I hope you guys are clear on the NoSQL fundamentals and the CAP theorem itself. And once this is clear, then now we can go into Cassandra in detail. What is Cassandra and how the whole thing works.
Yeah.
Okay.
Sudesh, when is the next session?
I think next will be on Saturday next week. Divakar will coordinate that, and I also need to know the details from Divakar only. So Divakar will let me know. Okay.
Yep. Thank you.
Thanks.
Thank you.
I'll stop it now. Thanks. Bye.
The organizer has